Phones evolved from bricks to supercomputers in 20 years because they are defined by software. A broken screen or lagging app can be fixed with a download, but a robot that falls over cannot be patched like an operating system. This distinction creates the central confusion of our time. We expect human-like robots to arrive at the same speed as smartphone features. The reality is far more complex and physically constrained. Smartphone evolution relies on rapid software iteration within fixed physical constraints, whereas humanoid robotics requires solving simultaneous physics challenges before advanced behaviors can emerge. While a phone screen remains a flat glass rectangle regardless of how much code runs inside it, a walking robot must constantly manage its own center of gravity against the chaotic forces of friction and momentum. The public expects robot evolution to follow Moore's law like processors or screens. This belief is false because you cannot update a hydraulic actuator with an iOS patch. A broken leg requires mechanical repair, not a software download. Consider the Nimro OP platform, where researchers including Philip Allgaier, Max Schwartz, Cordio Pastrana, Sebastian Schuler, Marcel Masura, and Sven Benke demonstrated that even with advanced middleware for behavior generation, robots must first master basic locomotion on human-scale environments. This hurdle took decades to clear compared to the years it took smartphones to become ubiquitous. The work was presented at a workshop where multiple authors refined their approach over 6 months, showing how iterative software development is impossible without solving the mechanical foundation first. The mechanics of walking are infinitely harder than they look because every step involves balancing an entire body weight on unstable surfaces. A pivotal study on the Boston Dynamics Atlas robot demonstrates why software alone cannot fix movement. Even with advanced control algorithms, walking is limited by mechanical friction and balance physics rather than code logic. The system requires a whole-body momentum-based control algorithm to maintain stability when stepping on partial footholds like small rocks or line contacts. Unlike a phone that can instantly re-render a user interface, Atlas must physically calculate center of pressure shifts and upper body angular momentum in real time to avoid falling. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a massive gap between our perception of AI intelligence and the physical reality of machine movement. While generative models now allow for complex interaction and high-level decision-making, these brains are useless if the body cannot stand up long enough to execute them. A 2024 review notes that while humanoids appeared roughly 60 years ago, we are only now beginning to see them exhibit useful senses and behaviors after decades of trial and error. The DARPA Robotics Challenge, launched in 2012, was intended as a catalyst for disaster robotics, but ultimately exposed that despite improved AI, robots still struggle with fine motor control and dynamic balance on uneven terrain. The industry is already reacting to this reality by pivoting away from the humanoid race because it is not yet viable for scale. Hello Robot, a company initially exploring human-like designs, has abandoned that path to focus on their wheeled robot, Stretch 4. CEO Matt Mackey notes that legged robots suffer from mechanical fragility and high costs in unstructured environments like homes, whereas wheeled platforms offer immediate safety and reliability. This shift confirms that the phone model of rapid iteration does not apply when hardware failure is a physical reality rather than a software bug. If we believe the phone analogy, we expect human-like robots to be common household items by 2030. The market correction shows this expectation is misplaced. Even with massive investment and hype, building functional hardware takes time that far exceeds software development cycles. Figure AIs. Figure 01 was often cited as a breakthrough for its speed, taking 12 months to move from concept to dynamic walking in October of 2023. While impressive to the public, this timeline underscores that rapid progress in robotics still means years of mechanical prototyping and testing. In contrast, smartphone features can be deployed via an over-the-air update overnight without any physical changes to the device itself. The speed difference between hardware and software is the core bottleneck preventing human-like movement despite AI progress. We have built intelligent minds for our machines that are ready to work tomorrow, but their bodies are still in kindergarten when it comes to navigating a messy world. The most immediate impact of this technology will not be human-like assistants doing laundry or walking upstairs like people by 2030. Instead, the future lies in specialized machines that leverage AI for specific tasks without the burden of bipedal locomotion. Understanding that smart software does not equal capable hardware helps us distinguish between marketing hype and deployable reality. We are seeing a separation where wheeled robots handle logistics efficiently while humanoid prototypes remain confined to controlled labs or highly structured industrial settings. The bottleneck is not artificial intelligence, it is our inability to replicate the energy efficiency and adaptability of biological legs with current actuator technology. The stakes for this confusion are high, because unrealistic expectations lead to wasted investment and delayed innovation in areas where robots can actually help right now. If we continue to chase human-like movement as a prerequisite for utility, we ignore the machines that could be transforming our world today. The engineering reality is clear. Until we solve the physics of walking with the same ease as software updates, our expectations must remain grounded in what is mechanically possible rather than what looks good in a demo video. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.